Hello everyone, this is Safdar Jamil and I'll be presenting the Exploring Data Deduplication in LSM tree-based key value stores today. This figure shows the overall storage hierarchy of LSM-based key value stores, where each operation is first served by memory components and then moved to storage layer. Compaction operation is performed to maintain the structure of the LSM tree, and because of that, it suffers from two major problems: high write and space amplification. To solve these problems, there have been several works, but none of the work has explored data duplication. Data duplication can be a novel way to mitigate write and space amplification, as multiple SS tables or a portion of SS table can be duplicated. By considering value-based deduplication, the total size of the primary storage can be reduced and hence write and space amplification. For that, we ask basic questions from ourselves. How to manage the deduplication overhead, as it comes with performance overhead from deduplication steps and space overhead from deduplication metadata. What type of deduplication technique to adopt, inline or offline, and most importantly, where to apply deduplication in LSM-tree. To clearly investigate deduplication benefits in LSM-tree, we explored two different approaches. First, inline deduplication at memtable. Here we intercept the write request and perform deduplication steps before updating the memtable. As inline deduplication is performed, less amount of data will be written to the memtable, hence less data at all levels of LSM-tree. For deduplication of metadata, we introduce chunk information table, which manages the fingerprint of the value part, list of the corresponding parent keys, its reference count, and location of the value. Let's look at the right example. When a put request comes, it is first written to the wall for maintaining the failure consistency, and then move to the deduplication layer, where we first perform fingerprinting, followed by duplicate detection, and then update the metadata at CID. After that, key value pair is updated at the memtable based on the deduplication results. Once the memtable is full, it is converted into immutable memtable, followed by dedup metadata update, and then follow rest of the LSM tree steps. Every time a key value pair is updated, its metadata is updated in the chunk information table, which leads to two major limitations of this approach: high performance overhead due to deduplication steps, such as fingerprinting, and constant metadata update or traversal. It can be observed from the graph that the performance drop with deduplication at memtable is severe and not acceptable. The second challenge is regarding the inconsistency issue, which occurs due to in-place update operations. Let's understand it through example. We already have some key value pair in memtable and metadata at chunk information table. Now, if an update operation is performed for K1, it will follow the same steps as explained before, writing to wall and then going to deduplication layer. As the value part is unique, a new entry is updated in the CID, followed by updating the metadata and memtable. It will update K1's value in place, and hence our metadata for K2 will point to an invalid value, which is an inconsistent state for dedup metadata and memtable both. To mitigate these problems, we propose Delta KV, which is an offline deduplication enabled LSM tree-based key value store. In Delta KV, we delay deduplication to flush operation when immutable memtables are first written to SS tables. Background threads perform deduplication, which leads to no interference to foreground IOs, hence less effect on performance. We mitigate inconsistency issue by delaying deduplication for immutable data instead of mutable data. For further optimization, we divide the metadata into two structures: value information table, which only serves the write operations, and B plus tree, which serves the read operations. Let's look at the example. Write request follows the same path, writing to wall and then writing to memtable. Once the memtable is full, it is converted into immutable memtable, and as the threshold meets for the flush operation, it is triggered. And from there, every key value pair goes through the deduplication layer, where deduplication steps are followed and dedup metadata is updated at value information table, and unique values are written to the level 0's SS tables. In parallel, a B plus tree is constructed following the keys and corresponding location of the values. For the preliminary evaluation, we present the results of value information table integration at delta KV. It can be observed that delta KV has similar performance as baseline RocksDB and outperforms memdedup. To conclude this presentation, we present the exploration of data deduplication in LSM tree with two approaches: inline deduplication at memtable and delta KV offline deduplication at flush operation. Thank you very much for listening to my presentation, and please feel free to contact me for any questions.